So I'll start recording the class. So let's go. So in today's class, previous class, we discussed electrostatics, where we discussed method of charging. We also discussed Coulomb's law and how to apply Coulomb's law. Good. So today, what we're looking at was electric field. If I ask you to define electric field, how do you define it? Tell us, what's an electric field?
Electric field.
Yes.
It is space,
Okay.
right? Or an area where you have, or where electric charges are concentrated.
Okay, good. Is that a definition?
Yeah.
You tried. Okay, basically, when we're talking about electric field, it is a region of space around a charged object. A region of space around what? Around a charged object. And this is how we calculate electric field. We say, okay, electric field E is equal to, we say the force per unit charge. Are we together?
Yeah.
Yeah, that's electric field. Force per unit charge. Exactly. Okay, good. Now, remember, the unit of force is Newton. Why the unit of charge is what? Coulomb. So the unit of this is Newton per Coulomb. These are the magnitude of what? Electric field. Now, pay attention to something that, you see, when we are talking about electric field, how do we detect it? How do we detect electric field? You see, pay attention to what the presence of electric field is can be detected by placing a test charge. The presence of electric field, what did I say? The presence
of electric field.
Of what? Electric field. The presence of electric field can be what?
Detected using
a
point charge.
No, not point charge, test charge. What do I call it?
Test charge.
Exactly. From the name test. We want to use, you see, the behavior of this test charge will make us know that, oh, electric field is present in this region. Exactly. So we use a test charge to detect what? To detect electric field. Now let's take for instance. Now observe. Let me see that, okay, there is a charge here. And let me call the charge Q0. Let me say there's a positive charge here with charge Q0. Now, let me say that, okay, we now have a particular test charge. And let me call that test charge Q. Okay, I'm coming. Let me say this is the charge Q. And we have a particular test charge, which has a charge of, let me say, a very small charge actually. It is small. Let's say that's very small charge like this. And this is what? Charge Q0. Q0, I'm using Q0 for the test charge. This is the test charge. Good. And they are distance r apart. They are distance r apart from each other. Good. Now, if you observe what is going on here, check. Take a look. Pay attention. Look at the charge, you can observe that the charge is what? Positive, right?
Yeah.
Exactly. Now check. If this test charge Q0 is actually positive, let me even put it there, is actually positive. Now, what will happen? Observe that, don't forget Coulomb's law. Unlike charges, remember, unlike charges will like charges will repel each other. So those forces will be directed away from each other. So if you observe the electric force on Q0 that was exerted by this Q will be directed in this direction, right? We go in this direction. Good. F prime. Good. F bar. Exactly. This is what the electric, and the electric force is equal to, remember, K, Q, Q0. I mean, all over what? Square. Exactly. Good. Exactly. These are what? These are our electric force because they have the same charge. You can see the way it will direct. Good. Okay, let us take on the other hand. Assuming I have a charge here, and this has what? A negative sign, and this is our charge Q. You see this charge Q, we can call it point charge or a source charge. This is what we want to test is electric field. So let me say this one is a what? Negative charge now, Q, and I have another one here, which is what? Q0, which is now in this case now is now negative. Now, what did you observe? What you observe that They have some distance apart, surely. Now you observe that what the force will be in opposite direction. Don't forget, these are, hold on, please. Hold on. This is positive charge. Good. Now, observe. What will be the effect of the force exerted by this on this? What will be the effect? You observe that the force will be directed this way because like charges will always attract each other. How together? This is the force. Good. And that's equal to, remember, KQQ naught over R square exactly times the position what vector. Good. Now, what do we now see here? Now, pay attention that the electric field created by a positive charge, we always radiate outward. We always radiate what?
Outward.
For example, check something. If you understand this particular point, let me assume this is a positive charge. Pay attention. Let's assume this is a positive charge. I want to find the electric field created by this source charge at a point, let me say at a point P here. Observe. I want to look at what the electric field created at a point what? At a point P. Now pay attention. Because this is a positive charge, the electric field it will create around this point will go away from it this way. That is, check. The electric, if it is positive charge, the electric field will be directed outward. Out together. This is that. Exactly. The electric field E will be directed outward of a positive charge, and that is what E bar. On the other hand, if I have a negative charge, I want to find the electric field at a point P. Because it is a negative charge, the electric field will be directed what? Towards it. Are you together?
Yes.
The electric field, it means that you've now known how the direction will look like now. If you are looking at the direction at a point and the charge that you want to detect is presence, look at it, it's positive. The electric field E will be going outward. Okay, let me take for instance now, check this thing out. Look at this point. Let me say I have a charge here. This is Q1. And I have another charge here, which is what? Q2. Now, look at this point. Let me say this is point P now. How will the direction of the electric field go? Now, check. Relative to this positive charge here, what will be the direction of the electric field due to the presence of this Q1 at this P? What will be the direction? The direction what? Go this way. Are we together?
Okay.
That's E1. Yes, you can say go this way. Just know the direction will be like this. We go away. We'll be
outward.
Yes, this outward. Have you seen it? Because this line continues. Yes, exactly. Now, if you want to look at this one now, the direction of the electric field will what? Like, how will it be? Is it what? Inward. All together?
Yes.
Do you now understand it like that? Do you get it?
Yeah.
Okay. So take notes. If it is positive, it will be directed away. If it is negative, it is directed towards it. Okay. Because just take note of this part. If you have a positive charge, the electric field will be radiated outward of it. Outward. Are we together?
Yes.
But if it is negative charge, it will what? Inward. It will what? Inward. Inward. Exactly. Inward. So this one will guide you inward, and that's it. Good. And pay attention. How do we find electric field? Remember that we say our electric field is equals to what? The force per unit charge. Now pay attention. Which charge are we referring to? Is it the source charge or the test charge? Which charge are we referring to? Hello. It is the what? What charge is this? It is the what? What is it?
Test charge.
No, the source charge. I will explain why. The source charge, or you say point charge. Why? Let me explain something. Let me just use that source charge because that word is really easy. The source charge. Why? Let me tell you. Remember that Q is the one that, the presence of this Q naught, what is it doing? It's only just to detect. The purpose of this thing is just to detect the presence of electric field. Are we together?
Yes.
Exactly. Just to detect. So it's not like it will be in this particular formula. Okay. It's just to detect the presence of the electric field. Now let's go. Don't forget that by Coulomb's law, what is F? F is what? K Q naught over R square, right?
Yes.
Exactly. Over R square, and we have our position vector. Now, how do we now find electric field? Don't forget, it's force per unit charge, right?
Mm.
Good. Now, what do we now do for you?
So
What
you put KQ on KQ Q naught over R squared.
exactly? Yeah.
Replace another F there.
Yes. Please do that on phone. Okay. So what do we have?
So you have F no KQ Q naught over R squared over
Okay.
Q.
Q naught over R square times this position vector, right?
Yes.
Good. I'm coming. Now,
So
what
why
do
do
I
you have
use?
that position vector again?
Remember, I'm using it in vector form. Okay.
Okay.
Yeah. So now pay attention. What do I represent with Q? What do I represent with Q naught?
Q naught.
Hmm.
Hmm?
What do I represent with Q and which one is Q naught?
Um.
I'm coming, please. Give me some second. I'm coming. Give me some 4 minutes. Something is malfunctioning here. I'm coming. Disturbing this thing.
Okay.
Okay, pay attention. Okay, pay attention. Oh, pay attention. Now, let's continue. So where am I? We are looking at this electric charge, right? Good. Okay, let me take one thing back. I'm coming. Let me take back something. Something I want to take back. I'm coming. Okay, pay attention. Remember, I told us that this Q naught is used to detect the charge, right?
Yes.
Exactly. So if I want to define that electric field, remember, I'm saying the electric force exerted divided by the charge I'm trying to look at, like the charge I'm trying to like experience the electric field on, which is Q naught. All together?
Okay.
Good. And don't forget from Coulomb's law, we have F equal to KQQ naught over R square, are you there? Times our
Mm.
position vector. So this will give me what? If I use this order, I have KQQ naught over R square times position vector, then times 1 over Q naught. Because I'm using
Yes.
this, remember exactly. So this Q naught cancels out each other. So therefore, my electric field in vector form is KQ over R square. But remember, I told you that I don't solve with this vector form because it's not really that easy, like I told you. The easiest one is just to use resolution. So I'll be looking at this now, if I want to say what's the electric field in scalar form? KQ over R square. Are we together?
Yes.
Good. This is when we want to find the magnitude of the electric field. Don't worry. If we want to find the direction, that's another solving that I'm going to teach you. Now, in summary, take note of something that, let's say we have an electric field created by this charge. Let me say, remember that it should be outside of this direction. Now, if I place a positive charge in this field, it will also accelerate in the same direction. Are we together?
Yeah.
But if I place a negative charge in the field, what happens? It goes what? In negative direction. Okay?
Yes, sir.
Goes in opposite there exactly. So that's that for that. That's that for what? For that. Good. Now, since we've learned this thing, okay. And we've learned that Checo. We've learned all this. We've looked at the direction. Okay, let us now work on some problem. Let's work on some problem. So let me start with simple problem. So we want to look at now electric field. If you understand Coulomb's law very well, this one will be so easy for you. Electric field due to two charges. Due to two charges. No, check it out. I will actually send this question to you. All together?
Yes, sir.
I'll send this question to you, don't worry. So the question is talking about, I will read it after I draw this diagram. Okay, so because of time, so I just. Okay. Good. So you have this point P. And that point P has a distance of y. This point here is the origin, 0, 0. And you have a charge here. And that charge is what? Positive charge. And you have a charge here. And that charge is the negative charge. The distance of this positive charge is labeled as Q1. Okay, this positive charge is labeled as Q1. I'm coming. This positive charge is labeled as Q1, and this one obviously Q2. This distance from here to the origin is A, and that is B. In fact, without the question, this diagram is enough to tell you something. Pay attention. I'll do some interpretation for you. So here we have this triangle. Here we have this triangle. Okay, now I have Y, and surely this is my x-axis. Good. Now pay attention to me. You see, how do we find the electric field created by Q1 and Q2 at this point P? There's a point P here that we are trying to find the electric field. This is the point P. How do we find the electric field? Now pay attention to me. This is the question. They said charges Q1 and Q2 are located on the x-axis at a distance A and B respectively from the origin, as shown below. Look at it here. Distance of A and B respectively, you can observe. If you observe, you see that what B is much more than A. Looking at the diagram, right?
Mm-hmm.
Good. It's kind of, I'm just kind of a broken line. Good. I'm kind of a broken line. Good. Now that what, find the components of the net electric field at point P, which is at a coordinate 0, y. What meaning of coordinate 0, y? It means that that point P is on the y-axis. Are we together?
Yes.
Exactly. So what do we want to find? The net electric. Remember that Q1, we create some electric field at P. Also, chat Q2, we create some electric field at P. So what is now the net electric field? That's what they are telling you to find. Now, pay attention. Don't forget that since Q1 is a positive charge, the electric field will be directed in what direction? This way, right? Away from it, right? Good. So this direction away. So this will be the electric field E1. Exactly. Also, because Q2 is a negative charge, the electric will be directed what? In this direction, right? Closer to
Yes.
it. Exactly. It will point towards it. Good. So this is my what? E2. Exactly. That is it. Now pay attention. In the question, you were given some angle. The angle here is phi, and the angle here is theta. Now, if you are going to be resolving the forces, surely you will resolve forces here. You'll be needing some angles. Let me say, put this broken line here to the horizontal. Put it here. Pay attention. Trace this line. Look at this line I'm pointing at, this particular line. Trace that line like this. If you observe, looking at this line, what angle is it making with the horizontal? Phi, right?
Yeah.
It means that this same line, blue line, we also make line phi with the horizontal. Yeah, since this one is making phi with the, it means that what all points on this line, since it's a straight line, it will make angle phi with the horizontal. Similarly, looking at this line, it makes theta with the horizontal line. Therefore, it also makes theta with the horizontal line here. So that is it. Now, let us now solve. Pay attention. Look at your electric field, A1. Remember that, firstly, let's find the magnitude of the electric field, just like we did on Coulomb's law. Now, don't forget that what E1 is equal to what? KQ1 over R squared. All together?
Yes.
Good. KQ1 over what? Over R squared. That is the electric field at this point P. We want to find the effect of this electric field at this point, what? Point P. Good. Now, pay attention. So this KQ1 over what? Over R squared. That R here, that let me say this one is R1, and then this one was R2. So this was R1 squared. And don't forget, mathematically, what is R? This is a right angle triangle. My R here will be equal to square root of A squared plus Y squared. So since this one has a square, R1 square will be equal to A squared plus Y squared. We are squaring both sides. So therefore, my answer KQ1 all over A squared plus Y squared. That's the magnitude of what? The electric field E1. Similarly, let's find the magnitude of the electric field E2. What do we have? KQ2 over R2 squared. And that will be equal to what? I have KQ2 over 17 here. I'll have what? B squared plus Y squared. Exactly, because our R2 here is also equal to square root of B squared plus Y squared. So therefore, my R2 squared is B squared plus Y squared. Good, that's what I have. Good. I have Q1, I have Q2. Nice. So since I have their magnitude, the next thing is that what? Let me go and resolve this E1. If I resolve E1 to the horizontal, what will I have? Now, observe, look at it from here. See, E1, I now want to find in vector form. Now, pay attention. Don't forget, if I resolve it to the x-axis, I'll be having E1, the magnitude, then cos phi, then I. And remember, if I resolve it to the what? To the horizontal, you observe that it will be facing this direction. That's positive x-axis. If I resolve it to the vertical, it will be facing this upper direction. That's y-axis. So positive E1 sine phi G. That's what I have there. Next one, I want to find what? E2. What do I have? E2 is what? Now check what. If I resolve E2 to the vertical and to the horizontal, it's be facing here. That's positive. So I have E2 cos theta I. Then if I resolve it to the horizontal to the vertical, to be facing this down direction, and that down direction is negative y direction. So I'll be having minus E2 sine theta G. So to now find the net force, check. To find the net force, the net electric field is the vector sum of E1 and E2. So don't forget that if you find remember the net force, the net force we have, by the time I add all these things together, the x components of the net force will be equal to this one and this one, right?
Yes.
Exactly. To what? E1 cos this plus E2 cos theta. That will be the what? X component. Also, the y component of the net electric field will be equal to E1 sine phi minus E2 sine theta. Exactly. So that's how we do. So that's how we can just find the electric field. Now, another question that come up is this. Now, let us look at case B. This case 1, where A is not equal to B. That's case 1. Let's look at case B, whereby Q1, chart Q1 and chart Q2 are equal. Also, A is equals to B. Chart Q1 and Q2 are equal. Also, A equal to B. How do we solve that case? What do we do? What do we do? Now, come back to this formula. Are we together?
Yeah.
Okay, what do we now do? If you observe, check something out though. I have a point P here, observe. And I have my E1. Please look at this one carefully. Let me use another ink to explain this fact. Now, check it out though. Remember this point P. And I have Q1 directed this way. I have Q2 directed this way. And remember, they have some angles to the horizontal. Now, pay attention. If I resolve E1 to the vertical, I'll be having something like this. This is the E1 in the Y direction. And remember, check. A is not equal to B. If A is not equal to B, hello, are you there?
Yes.
If A is not equal to B, see, let me say, if A is not equal to B like this, it means that this line will be exactly at the midpoint. Yes or yes?
Yes, sir.
Good. So if it be exactly at the midpoint, take note, these two angles here will be equal. These two angles here will be what?
Equal.
Equal. Nice. So they are not, let me now say they are not equal to theta, theta. So this guy is theta. This one is also theta. Also, check Q1 and Q2 are equal. If that is equal, it means that this electric field, the magnitude E1 and E2 will also be equal. Check, since Q1 and Q2 are equal, you will see, and they are now at the same distance. So R1 and R2 will also be equal. Please, if there's a question you need to ask, just ask. R1 and R2, this case 2, let me put it here. R1 and R2 are equal. Let me say they are equal to R. Good, because by the time this guy be at the midpoint now, you see this distance and this distance are equal. Just like I was saying isosceles triangle.
Yeah.
It's not equal isosceles triangle. Exactly. Now, so since they are not equal, if I resolve E1, I'll have E1y. If I resolve E2, I'll have what? E2y. If you observe, E1 and E2 will cancel out each other. This and this, it means that what? We don't have any y component. So if I resolve this to the x-axis, I'll have E1 to the E1x to the x-axis, I'll have E2x. So it means that my total net force should be the one of the x component. Why y components will cancel out each other? Are you saying that?
Yes.
So what do we now do? Here, let's go. Our E1, firstly, the magnitude. Our E1 will be equal to KQ. Since Q1 and Q2 are equal, I'll call them Q. KQ over, since R1 and R2 are equal, I'll call them what? R. Let me call this Q. So over R squared. So this is what I have. And what is R?
R is
A squared plus Y squared. I mean, now, don't worry,
Yep.
continue this way. And what's E2? KQ over R squared. And that will give me what? KQ. No need to put Q1 and Q2. KQ over R squared. Remember, the R are both equal. So I'll just say A squared plus Y squared. Or if you like, you can use B squared plus Y squared. Remember, A and B are equal already. Now,
Yes.
after the next thing is that you want to remember we are using this component. So my total the net electric field will be equal to E1x plus E2x. There's nothing like Y component because the Y component has cancelled out each other. So therefore, my electric field, the next one now be equal to, what do we have? E1x is equal to what? Check. It will be what? E1. Then remember cos theta, right? Resolving
Yeah.
this cos theta. That's cos what? Cos theta plus kq over a square plus y square sine
Theta.
theta. Exactly. So my final answer here next will be equal to kq over a square plus y square, then cos theta plus sine theta. Cos
Okay.
theta plus sine theta. That will be the question. A and B are equal. Though I will send the question to you. The
Okay, sir.
question A, this and this are equal, A and B are equal, also theta and phi are equal. So that's the question. That's for B. Nice. Okay. Are you done with that?
Yes.
If you observe from that triangle, what is my cos theta? From that triangle, what is my cos theta? Check. If you check, what is my cos theta here? What you're having in one triangle and the other triangle are equal. So what's my cos theta?
Cos
Cos
theta.
theta is what?
I don't know.
Cos theta is what? Adjacent over hypotenuse. That's what? A over hypotenuse R. Are we together?
Okay.
Okay, good. What is sine theta? You can use one triangle to do opposite hypotenuse, which is what? Y, Abi?
Yeah, over theta. No, why over?
Over R. Are you there?
Okay.
Okay, good. All right. So that's what I have. So let's go. Wait, why am I having sine? This is cos. This cannot be sine. This is cos. Please be careful. This is cos, sorry. Because if you are resolving this, they are both cos theta. Now, how come you are using? Do you remember?
This side is.
If I resolve them to the
Adjacent
result,
over.
they are both cos theta. Okay?
The other place is adjacent. Oh.
Yeah. So this cos theta is also the same thing. Adjacent A over R. They are both cos theta, please don't forget. Mistake from my end. Sorry. So I have cos theta, cos theta. So everything I'm having is like 2 kq over a square plus this cos theta. So that will give me 2 kq over a square plus y square. What's my cos theta? A over R,
Over
right?
yes.
A over R. And my R is a square plus y square.
Okay.
So what I'm having here is now what? My net electric field will now be equal to what? What's it equal to? What's it equal to? It's now equal to what? 2akq over a square plus y square all square. Okay?
Yes.
Sorry. Wait, hold on. My R is equal to square root of a square plus y square. And what I'm having here is R square that is square root of. I'm not making a mistake in this thing. This way. So this is square root of a square plus y square. Are we together?
Yes.
Sorry. This is it. So I have 2akq over this raised to power 1 and this is power half is a square plus y square square root of 3 over 2. That is raised to power 3 over 2. This is the answer.
Okay.
in that setting. So this one will give you hints whenever you are solving any question. This you don't have to cram formula. These are the steps you are going to use to solve it. These are the steps you are going to use to solve it. That's for that. So I'll give you an assignment on this. You are going to solve it exactly this way. Okay. Firstly, you find the magnitudes and you resolve them and add them together. And take notes, please. You can see I'm always putting the magnitude of the charge Q, which means that if the charge is negative, we don't apply the negative sign. Okay. We account for the negative charge whenever we are looking at the direction. All right, that's that. So let us solve this question. This other question. Let me write this. Of the electric field. Are you ready?
Yes, sir.
So read the question.
A 200 microcoulombs is placed at the origin, and a minus 300 microcoulombs is placed 1 meters to the right of it. What is the magnitude and direction of the electric charge midway between the two charges and 30 meters to the right of the negative charge? Oh.
Okay, that's all. Now see what we have here. So we have this question. Let's bring out the picture. Okay, let's quickly draw our x-axis. Okay, since we are looking at right and left, it means that both charges should be at the x-axis. Now pay attention. So check. They said that check a plus 200 microcoulomb is placed at the origin. At the origin, what does that mean? Well, let me call this the origin 0, 0. So this is the charge. So let me say this is the charge Q1, which is 200 microcoulomb. Is placed at the origin 0, 0. Now pay attention. They said that what, and a minus 300 microcoulomb is placed 1 meter to the right of it. So let me say this entire length is the 1 meter to the right. So you're having from here to here is 1 meter. So this is what I have. This is another charge, Q2. And that's minus 300 microcoulomb placed to the right. What is the magnitude and direction of the electric field midway between the two charges? Now check. So you have to find the magnitude of this electric field at this point. This is the point P. You want to find the magnitude of what electric field. Now that's that what, okay, that's what we have first. Now say also at 30 meters, but let us leave that one and solve this. Now pay attention. What would be the, if this is the positive charge, what would be the effect of this charge on this point? What would be the direction of the electric field? If it's a positive charge, the direction of the electric field will be away from it, and that's E1. Are we together?
Yes.
And because this is a negative charge, the electric field was towards it, that is E2. It means that my net electric field will be equal to what? E1 plus
plus
E2. All together?
yes.
Positive, exactly. Okay, so before we do anything, let's calculate the magnitude of the electric field. What is E1? The magnitude of electric field E1. Remember, KQ over R square. So I have K. What is my Q? Remember, K is 9 times 10 is power 9, or you say 8.99. So let me use 9 times 10 is power 9. What is my Q? 200. All over what distance? 0.5, 0.5. So 0.5 square. All together?
Yes.
So you get an answer for this. So E2 is also calculated the same way. Now check. Remember that Q2 is negative, right?
Yes.
But when I'm solving, I won't put that negative to find the what. Yeah, because I've already account for the negative with this. Yeah. So let's go. What do we have? Times 300. Remember, micro is 10 is power minus 6. This 10 is
Yeah.
power 6. Then all over 0.5 square. So what do we have here?
The first one is not sure. I think it's 7,200,000.
Do it in standard form. You don't have calculator that is standard form.
No, that's 7.2 times 10 power 1, 2, 3, 4, 5, 6.
7 point what?
0.2 times 10 power 6.
6 Newton per coulomb. Next, calculate this.
Next
What do you
one
have?
is 9 times 300. Okay, nice. 27
Okay.
times 1,000. I'm coming. Divided by 0.5 square. That one is 10.8 times 10 raised to power
10 points.
6.
You put the standard form.
1.08 times 10
Mhm.
raised to power 7.
Okay, this one is 10 is power 6, right?
Yes.
You can write this as 0.72 times 10 is power 7 Newton per coulomb. It's the same thing. All right,
Okay.
Newton per coulomb. So I've gotten the what? The magnitude. So how do we now find the vector form? Do not forget something. Sorry, next. Now we now want to include the direction now. Check. They are both positive. Do you know that?
Yes.
Exactly. So I'm adding both of them together. So they are both positive I, positive I. So let's go. What do we have? Add them together. What does that give you? 1.8
0.08. 1.80.
and 10 is power what?
7.
Newton per coulomb. That's my answer. To the right.
Okay.
To the right. So that's what I have. That's the electric field. Now that's the first question. The second question, that's that what? And 30 meter to the right. It means that the next point is this point. We want to find the electric field at this point. Check. At this point, 0.3 meter to the right of the negative charge. So this is another point. Let me say this point P prime. Now, if you observe, the electric field created by Q2 at this point will be greater than that of the electric field created by Q1 because Q2 is closer to this point. Do you understand?
Yes.
So the electric field, because let me tell you something. The closer the distance, the greater the electric field. Look at the formula, KQ over R square. So like this R square has more effect on the electric field than the magnitude of the charge. It has more effect. It has what? It has more effect. So let's go. What do we do? Or you solve this? I should solve it.
Yes.
Okay, let's go. Now, what will be the effect of Q1? I'm coming. What will be the effect of Q1? Remember, Q1 is positive, it will always go away, and that's E1. If Q2 is negative, it will turn back this way, that's E2. All together?
Yes.
It means that for this example, for this second example, my E net will be equal to E1, are you there? Minus E2. Why am I saying minus E2? Because they are in opposite direction. Remember, they are vector. We should also
Yeah.
account for the direction, right?
Mm-hmm.
All right. I have, okay, let us now calculate our magnitude, E1 and E2. E1 equal to 1 over R square. 9 times 10 to the power of 9 times 200 times 10 is per minus 6. Now, what the distance? The distance has changed.
Zero
Distance
point.
of charge Q1 from this point P is 1 plus 0.3, and that's 1.3. Yes or yes? Do you hear it is 1.3?
No.
Okay, look at it. You are looking at distance from here to this point where you want to find the electric field. They have changed the point for you already. Before it was at the midpoint of the two charges. Now, the point that you want to find the electric field at has been changed to 0.3 meter to the right of charge Q2. So now, what distance of charge Q1 from point P here? From here to here is 1 plus
Okay, for
0.3.
zero
That will
point
give
three.
you
Okay.
exactly
Okay.
1.3. So this is
Okay.
1.3 square. So you get an answer. So E2 is KQ2 over R square, and that's 9 times 10 to the power 9. And what's Q2? Q2 is, remove the minus, times 10 to the power minus 6. Now, what distance of Q2 to point P prime? 0.3, right?
Because 0 point. Okay.
What's our answer here?
For that first one, of 1/8 multiplied by 1000 also divided by 1.3 squared. That's kind of weird. 1065088.757.
Put it in standard form.
That'll be 1.065088.
Mm-hmm. 0.65 times 10 is power.
Times 10 is to power maybe 3.
They're not telling me this answer. So if it is wrong, hold on, please give me some second. You are not telling me the answer. So if it is wrong, it is on you. Yeah. What's the answer?
Times 10 is to power 3.
3. Mm-hmm.
Yes.
Newton per coulomb. All right. Next one.
Okay. That'll be 27 multiplied by 1000. So answer divided by 0.3 squared. Okay, this is 3.0
Mm-hmm.
times 10 raised to power
3.0. Just 3.0.
yeah
Times 10
times
is
10
power.
raised to power 1 2 3 4 5 7.
Are you sure?
Yes, it gave me 30 million when I did it right standard form.
Okay. Newton per coulomb, right?
Yes.
Wait, what was the exact answer this gave you? 9 times 10 is power 9 times 20 times 10 is power minus 6. Are you putting 10 is power minus 6 there?
Yeah, that one gave let me do it again.
Do it again
1
here.
8 multiplied by 1000. Then answer divided by 1.3 squared. 1065088
Mm-hmm.
0.757.
You are wrong here. It should be the standard form. 1, 2, 3, 4, 5, 6.
Oh,
So that's times 10 is power what? 6. So I can write it as. I don't know you made a mistake there. I thought as much. Now check. Here it should be like I can write it as 0.106
5 times 10
times 10
plus
is power 7 Newton per coulomb. And check. Pay attention to something. We want to find the net electric field. And for this one, it is what? E1 minus E2, right?
yes.
So what's my E1? 0.1065 times 10 is power 7 minus 3 times 10 is power. If you observe, let me tell you something. See, you observe that Q2 has a greater influence on this point P prime than this Q1. Do you know that?
Yes, because
Exactly. That is why the total electric field will be negative. Altogether,
okay.
it will be negative. You can say to be pointing towards what? Q2 to be negative. So what do we have here? Yeah. I could just say what 0.1065 minus
Yeah,
3.
that's minus 2.8935.
8989.
35.
No, times 10 is power 7.
7.
It
Okay.
means that your electric field is 2.89 times 10 is power 7 to the left. So if you remove
Okay.
the minus, just say to the left. So it's like 2.8789 times 10 is power 7 Newton per coulomb to the left. To the left.
Yes, to the
Exactly.
left.
To the left. Good. That's our answer. So that's that for that. I'll send an assignment to you. So after this, the next thing we are going to now be doing is to be about, okay, the next thing we are going to be doing will now be about charge distribution. Charge distribution. Charge distribution. Charge distribution. Now, when we are talking about charge distribution, in a simple word, we are talking about collection of charges. Talking about what? Collection of what?
Charges.
Collection of, exactly. Collection of what? Of charges. Now, pay attention that this collection of charges could be divided into two. It can be discrete charges, where it is possible for us to count them. And we have continuous charges, where it is impossible for us to count them altogether. Remember, I told you something in statistics that discrete are something of integer, whole number that you can count altogether.
Yes, sir.
Continuous, exactly. Okay. All right. If I'm looking at this script now, for example, I can say, okay, looking at this one now, I have 5 nanocoulomb here. I have 5 nanocoulomb here. I can say, okay, at this other point, I have 3 nanocoulomb, and so on like that. Those are distributed to count the number of charges that are there. But for continuous, it is not possible. Okay?
Yes, sir.
Okay, good. So we are looking at this continuous one majorly. Now observe, if I have a line, pay attention, if I have a line and charge is evenly distributed on this line, check it out. Now pay attention, there is a particular word we call charge density. Called what?
Charge density.
Exactly, charge density. You see, when we are talking about density, we are talking about how crowded something is. That's the meaning of the word density. If you find a material that is more denser, it means that its atoms are crowded together. Okay?
Yes.
Yes, one of higher density means that the atoms are more crowded together. Exactly. If you observe, check. If I'm talking about charge density, don't forget it means like crowded. Let me put it in case you are studying. It means like you're looking at crowded. So if I'm saying charge density, it means like I'm looking at how crowded the charges are on this line. Are we together?
Yes, sir.
Okay, good. Okay, this is a straight line. So the first one we are going to be looking at is linear charge density. What do I call it? Linear charge density. Exactly. And linear charge density is what? The charge, the total charge Q divided by what? The length. The total charge per unit length. That's coulomb per meter. That will be the unit. What does this one mean? Pay attention. If I calculate the linear charge density here, and for example, let me say my answer is equal to 20 coulomb per meter. Remember that, check, the charges are evenly distributed on this line. If you observe the example, you can see.
Yes.
So since it is evenly distributed, it means that this 20 coulomb per meter means that if I move from here to here, for example, if this is 1 meter, the total amount of charges I'll be having will be what? 20 coulomb. And for every 1 meter you are moving, the total number of charge is 20 coulomb. Do you understand?
Yes, sir.
That is it. But let me now draw another line and show you another scenario. Look at this scenario whereby, check. Are they evenly distributed this way? Check. Are they evenly distributed this way?
Nope.
Please look at this. Remember, I'm looking at continuous distribution of charges. Now check. This line does not mean that what I'm saying here does not mean that there's no charge here. It does not. You know, this space is empty now.
Yes.
Don't feel there's no charge. Charges are that these charges, you know, they're spread out on this line. But the difference is that they are more crowded here than this other region. But charges are, you know, are spread continuously on the line. Okay.
Yes.
They are spread continuously, in an even manner, but yet they are crowded in one side and one side. Okay.
Yes,
Good.
sir.
Now let me now say that I calculate my linear charge density here to be. Let me see. I calculate this one to be 50 coulomb per meter. What does that mean? Pay attention. This one does not mean that if you move every 1 meter, you'll be getting 50 coulomb. No, because the charges are more crowded in one point than another. So it's just like, let me say, I pick my 1 meter here. You see, this 50 coulomb is just at this specific point. You can calculate another point now and get your charge to be 5 coulomb per meter just for this point. Are we together?
Yes. Okay.
Exactly. Because why is this one lesser? Because charges are less crowded around this region. Do you understand?
Yes, I get it.
Okay, that's for linear charge density. Now, the second charge distribution we are going to be looking at is this boy is making noise. Can you hear the voice of the small boy in the background?
No, sir.
Okay, yeah. Please hold on. So this is the first one, linear charge density. So the next one is what? Surface distribution. The next one is surface charge distribution. Now, let me say I have this surface. Let me say I have this surface, and charges are distributed on this surface also. Now, if I'm talking about surface, majorly I'll be looking at what area. So let me say the surface charge density is denoted by what sigma is equal to 10 coulomb per meter square. Let's say the formula for surface charge density is Q divided by area. Q divided by area. So it means that if I calculate this thing to be 10 coulomb per meter, that what for 1 meter square, for 1 area meter square, I'll be having 10 coulomb. Is that clear?
Yes.
And lastly, we want to be looking at the volume charge distribution. The volume charge distribution. So if you are solving the question, they say find the linear charge density, find the surface charge density, find the volume charge density. This is what you just do. So this one is denoted as rho. As rho. Let me say I have a cube, for example. This is like a volume. And charges are distributed on it. Of course, charges are distributed on it. Now, take note that the formula is charge divided by your volume, V. And this is what coulomb per meter cube. Nice. So see what I have here now. So if I calculate the volume charge density and I get something like, let me say 20 coulomb per meter cube, it means that for 1 meter cube volume you pick, it will be what you are going to be having 20 coulomb. Is that clear?
Yes, sir.
So that's about the charge distribution. So probably in our next class, we'll be looking at, let me just stop here. What we're going to be looking at in our next class will be electric field in some specific geometry, like in a charge ring, in some other, you understand?
Yes.
Yes, so then we're moving to Gauss law and the rest. So any question here, I'll send your assignment to you. Any question?
No, sir.
So we call it a day from you. I'll send the note to you. Bye.
Okay.